Okay, so we're going to go over Chapter 1, Section 4, Polynomial and Rational Functions. We're going to talk about properties of polynomial functions, polynomial regression using a calculator, properties of rational functions, application of polynomial and rational functions. And a polynomial function basically has a coefficient x to some power plus, and then we usually go downward from there. The leading coefficient, the number in front, the one with the highest exponent, that tells you the degree of the polynomial. Okay, and we'll look at some examples. The domain is a set of all reals. The range of odd degree is all reals. Even degree is a proper subset of reals. Constant function polynomial is 0. Linear function is degree 1. Quadratic polynomial is degree 2. So bottom line, we've gone over linear and quadratic already. A linear function, the highest exponent is just an x to the 1. That's a degree of 1. Quadratic, it has the squared, is a polynomial of degree 2. So we've already kind of started looking at this stuff. We're just going to look at some certain things, okay? If your degree of the polynomial is odd, it has some special characteristics. The odd degree polynomials cross the x-axis at least once. All odd degree polynomials with positive leading coefficients start negative and end positive. All odd degree polynomials with negative leading coefficients start positive and end negative. Even degrees never intersect the x-axis. Some even polynomials never intersect the x-axis. All even polynomials that start positive end positive and have positive leading coefficients. All even polynomials that start negative end negative and have negative leading coefficients. And as I go through these, I'll just point out what we're talking about. What's the degree of f of x equals x minus 2? What's the degree of that polynomial? 1. X to the 1. It's a linear. It's going to be going either upward or downward. We talked about linear before, but that is what a polynomial degree 1 would look like. Okay? And it's odd. 1. What's the degree of g of x equals x cubed minus 2x? 3. It's a third degree polynomial, and it's odd or even. Odd. When I say odd, you should already know that the ends are going to be opposite. Okay? Notice this one looks like it's going down, this one looks like it's going up. That's a property of being odd. Okay? Where it starts, where it ends, depends on the leading coefficient. Okay? If I had h of x equals x to the 5th minus 5x to the 3rd plus 4x plus 1, what's the degree of this polynomial? And it's odd, which means the ends are going to be the same or different? Different. Okay? And again, the nice thing about all of these, you can go to your calculator and graph every single one. Okay? So just pointing out some things that's nice to know. If you had f of x equals x squared minus 2x plus 2, what's the degree of that one? 2, which is even, which means both ends are going to be either up or down. And because we've done quadratics before, a is 1, so is it happy face or sad face? Which one? Happy face. Okay? They're going to match because they're even. These are just some things that are good observations. If we asked you g of x equals 2x to the 4 minus 4x squared plus x minus 1, what's the degree of this one? 4. 4 is even, which means they're going to match or they're not going to match? They're going to match, and the leading coefficient is 2, which is positive. Notice they're both going up. Okay, things about polynomials. And if I had h of x equals x to the 6 minus 7x to the 4 plus 14x squared minus x minus 5, what's the degree of this one? 6 is positive. Both ends are going to match. Both going up. We okay? So all these things are like, that's good. I know about that. So just quick review. Each odd degree polynomial graph starts negative and ended positive. All had positive leading coefficients. The ends of each odd degree polynomial moved in opposite directions. Each odd degree polynomial crossed the x-axis at least one time. Each even degree polynomial started positive and ended positive. All had positive leading coefficients. Some even degree polynomials crossed the axis, some did not. The ends of each even degree polynomial moved in the same direction. Other observations. No graph crossed the x-axis more times than the degree. So if the degree is 6, it will not cross more than 6. Changes in direction are limited to 1 less than the degree. Polynomials are continuous functions. Continuous means when you draw the graph, it's smooth, like you never take your pen off the paper. So if I had f of x equals 2 absolute of x over x, that's not continuous. There's a break in there. If I have h of x equals absolute x minus 3, the graph is continuous, but since it's a V, it has a sharp corner, it's not smooth. Continuous, but not smooth. And then the last one, g of x equals x squared minus 4x plus 5. That's quadratic. That would be a graph that is continuous and smooth. Again, all of this is review, refresher, just to get you thinking about polynomials again. In section 1.3, we looked at quadratic regression. Now we're going to look at some other regressions, and our graphing calculator is going to help us. Okay? So here's our example. The data table gives marriage and divorce rates per 1,000 population for selected years since 1960. Let X represent the number of years since 1960. Create a scatter plot for the data. Find a cubic regression this time, that models the marriage rate. So here's the deal, okay? We're looking at date, and we're looking at marriages. The more we do, the better we get at it. So I'm going to ask you to go to your calculator, and in list 1, we're going to put the dates. But we're not going to put 1960, 1970, 1980, 1990, 2000, 2010. We could. But the way the book likes it and the homework likes it, instead of calling it 1960, we're going to call it 0. And then what are we counting by? Tens. So we're going to put 0, 10, 20, 30, 40, 50 in list 1. And in list 2, we're going to put the marriages. 8.5, 10.6, 10.6, 9.8, 8.5, 6.8. So we should be getting very good with our calculator. Push stat, number 1 for edit, and we're going to put in list 1 and list 2. So everybody has a calculator at this point. We're sharing with somebody. Gotta have a calculator. Everything is calculator. Okay? Again, even though we cover it, doesn't mean you remember it. So we have to practice. Okay, so let's practice our calculator. Now, one thing we want to make sure is we have a clean calculator. So everybody for me, even if you're playing around with it, go to y equals. Make sure that plot 1, plot 2, plot 3 are not highlighted. If it's highlighted, go up to and hit enter. None of those should be highlighted. Make sure there's nothing in y1, nothing in y2, nothing in y3. Then, in list 1, we're going to put the years. In list 2, we're going to put the marriages. So to do that, we push stacked, number 1 for edit. Notice I have stuff in my list 1 and 2. So if I go to the top of list 1, hit clear, enter, that clears the list. Go to the top of list 2, hit clear, enter, that clears the list. Don't go to the top and hit delete. So does everybody have list 1 and list 2? Then we put 0, enter, 10, enter, 20, enter, 30, enter, 40, enter, 50, enter. And in list 2, 8.5, 10.6, 10.6, 9.8, 8.5, 6.8. So any questions on how to put the data in the calculator? Okay? Let's move away from the calculator for 1 minute, and let's make sure we understand the problem. What's going to go on my x-axis? Years. And I need to figure out what to start with and what to end with. So what do you think I should start with? 0. What do you think I should end with? Probably not exactly 50. We're going to go a little bit further, maybe 60. And what should we count by? 10, 20, 30, 40, 50, 60. This is really important because we're understanding we're going from 0 to 60 years out. My y-axis, the lowest is 6.8. So what should we start with? You can start with 5, 0 works, 5 works, but below 6.8, the highest is 10.6. So how high should we go? Like 12, counting by what? And again, no one's going to tell you this. You have to understand the data to figure that out. It doesn't have to be exactly the same, but a little bit above and a little bit below. This is our marriage. This will help us understand the problem. Understand what we're starting with, what we're ending with, what we're starting with, what we're ending with. So it's super important that we understand the problem, not just push buttons in the calculator. Okay? So going back to the calculator, step 1, put the data in the calculator. Check. Step 2, tell the calculator I want a scatter plot. So to get a scatter plot, everyone hit second y equals, second y equals. All of them should be off. We're going into plot 1. Turn it on by pushing enter on. Choose the first picture, which is scatter plot. Now again, I'm going a little faster because we've done this before. And when we do it, the faster we can go. If you're still confused on buttons, go back and watch the videos, go back and practice. Where's my X? Second 1 for list 1, enter. What's my Y? Second 2 for list 2. And then, do you want your dots to be boxes, pluses, or dots? I'm going to choose the box. Okay? So let's make sure we're all together. Does everyone have the data in list 1, list 2? Everyone turn their plot 1, chose scatter plot, list 1, list 2. Okay? Now, there is a shortcut if you hit zoom 9. If you hit zoom 9, it makes the window for you. I'm not using that shortcut right now. I think it's important for you to understand the data. It's important that you figured out what the scale should be. So together, we're going to make the scale based on what we did. So everybody hit the window button. Window, window. What is our X minimum? 0, enter. What's our X maximum? 60, enter. What's our X scale? 10, enter. Perfect. Y minimum? 5, enter. Y maximum? 12, enter. Y scale? Enter, then hit graph. Now, we're going to do cubic regression because they told us to do cubic regression, but in reality, we look at the dots and say, does that look like a line to you? No. Could it be quadratic? Maybe. They're going to tell us to do cubic. So normally we tell you which one to do, but in reality, you just do the one that fits the best. Okay, so we take a minute, make sure that we have it. If you are ready, and if you remember, the same way we do linear regression was the same way we do quadratic regression, which is the same way we do cubic regression. So see if you remember where cubic regression is. You could use okay? Now again, same way we did linear, the same way we did quadratic, the same way we did cubic, and the same way we're going to do logarithmic and some other ones. What button do I push? Stacked. To the right for calculate. All the regressions are here. We're not doing linear number 4, we're not doing quadratic number 5, we're doing cubic number 6. Okay? Now remember, we don't always use 1 and 2, but we can. But it wants to know X and Y. X is list 1, Y is list 2. If you have the older version, which is totally okay, and yours is just blinking, you have to put list 1, comma, which is above the 7, list 1, comma, list 2. Then hit enter, and everybody look up to see if it all matches. Did everybody get this? Everybody got this? Okay, now if you're missing the R squared, that's when we turn the diagnostic on. We'll review that later. I'll help you one by one. Okay, but for right now, does everyone have A, B, C, and D? And are they the same number? So the form is up top. Our job is just to plug in A for A, B for B, C for C, D for D. But stop. Be careful. Not a trick question, but important question. What's A? Oh, is it 8.7? No, and if you put 8.7, it's going to be wrong. This happens a lot with the calculator. What does e to the negative 5 mean? Start at the decimal, move left 5. Does that mean 5 zeros? No, it ends up being how many? 4 zeros. So let's write this down as a function. Let's call it m for marriage of x. And I would write it down as 0.123487 x cubed minus 0.0108 x squared plus 0.2907x plus 8.546. Now you're probably wondering, how many decimals do I need to go? And the answer I always give is appropriate. And you don't like that answer. You want to be told always 3, always 4. Generally 3 or 4, but to me it depends on the number. If I did 3 or 4 here, it would be 0. So it depends on the number. But let's make sure we have our graph labeled. 0 is 8.5, 10 is 10.6, 20 is 10.6, 30 is 9.8, 40 is 8.5, and 50 is 6.8. And then now, when I graph this line, what should the line do? Go through the dots or be close to the dots. So go to y equals, be very careful, and type that in. 0.123487. To do x cubed, it's x raised is above the division. 3. Move to the right to come back down. Minus 0.0108 x squared plus 0.2907 x plus 8.546. Enter. And when you're done, hit graph, and your line should go through your dots. Linear, quadratic, cubic, all the same stuff. Okay? As you're copying and writing that down, some of you said you didn't see the r squared. We took care of that last class, but let's do it again. If you didn't see the r squared, a one-time only thing, press second 0. So if you didn't see r squared, press second 0. Hold the down arrow down until you get to diagnostic on. Once you get to diagnostic on, put your little arrow on diagnostic on. Push enter and enter again. It looks like nothing happened, but let's do it again. Stat, calculate, cubic regression, list 1, list 2. Now you should see the r squared. And the r squared is important because the closer r squared is to 1, the better the fit is. Is this a pretty good fit? It's a really good fit. But once I teach you linear regression, they're all the same steps. They're all the same steps. Okay? Let's take a moment. Any questions on this one? Did everybody get it? Okay? Perfect. So, we made the scatter plot. All the steps in the slides, put the data in. List 1, list 2. Set up the scatter plot. Use plot 1. Notice they use Zoom 9. We made our own window. There's the dots. They did cubic regression just like we did it. They put the equation in. They're very careful in how they typed it in. Notice they have 8.7. They use the E symbol. We did the decimals, so don't really watch what they did. And you get your graph. Okay? Questions there? Linear, quadratic, cubic, all the same stuff. Okay? Something else we're going to talk about in this section is rational function. Rational function is a function that can be written as basically f of x equals, we have a numerator and we have a denominator. If we call n of x the numerator, d of x the denominator, they're two polynomials. The domain is a set of all reals in which d of x is not equal to 0. Remember, we cannot have 0 in the denominator. It's undefined. Rational functions are quotients. A polynomial function, basically a polynomial on top and a polynomial on the bottom. So if I had the numerator is x minus 3 and the denominator is x minus 2, the rational function would be f of x equals x minus 3 over x minus 2. But before we move on, what can x not be? What could x not be?
3. Oh, 2.
2.
I can see.
Yeah, 2, because 2 minus 2 is 0. 0, the denominator is undefined. So this would work for everything except 2, which means something's going on at 2, which we'll talk about in a little bit. Okay? So everything except 2 is in the domain. A vertical asymptote of rational function is a line of the form x equals h, which the graph of the function approaches but does not cross. So vertical asymptote is basically a vertical line where the graph does not touch. So in these three examples, notice in the first example, f of x equals x minus 3 over x minus 2. What can x not be? 2. And what happens at 2? The graph comes really close but doesn't touch. It's undefined at 2. In the second example, be careful. This is why we did Appendix A. If you had f of x equals 8 over x squared minus 4, what can x not be?
2.
2 or negative 2. So number one, you can factor this, x minus 2, x plus 2. Or remember that x squared can be positive or negative. But notice we have two vertical asymptotes there. But if you don't know how to factor, we can't even have this conversation. That makes sense? That's why Appendix A is super important. Two vertical asymptotes. Here, these are not combined, so we can't really see, but there isn't a vertical asymptote. But we have this one. Does anybody know what that's called? It begins with an O. It ends with oblique. Oblique asymptote. Okay? An oblique asymptote. I'm talking about those little. Okay. Horizontal asymptote, same idea, but it's y equals. It's where the graph does not cross as both x increases and decreases without bound. So here, these examples, the first one has a horizontal asymptote at y equals 1. Now we're going to go through the rules in a minute, but let's back up. Vertical asymptotes is the number where the denominator is undefined. So how do you find vertical? You look at the denominator, what can it not be? How to find vertical? You look at the denominator, what can it not be? For horizontal, I'm about to go over the rules, so don't worry. But to figure out the rules, what's the degree of the top? What's the degree of the bottom? When they're the same, yes, you have a horizontal asymptote. It's the coefficient 1 over 1. What number's in front? 1. What number's in front? 1. What's 1 divided by 1? We have a horizontal asymptote at 1. And we'll go over the rules in a minute. The next one, there's a horizontal asymptote at y equals 0. Okay? Why is that? What's the degree of the top one? 0. What's the degree of the bottom? 2. When the degree of the numerator is lower than the degree of the denominator, yes, we have a horizontal asymptote, and it's always at 0. Always at 0. Top degree, lower than bottom degree, y equals 0 is horizontal, and the last one doesn't have a horizontal. But again, that one needs to be simplified. Okay? So here are the rules. And again, write these down. We're looking for, well, this is vertical one. For vertical, it's where the denominator is undefined. Vertical, where the denominator is undefined. Okay? The ones I really want you to note, and I'll read these real quick. For vertical asymptotes, if the denominator of a rational function has a degree n, the rational function can have no more than n vertical asymptotes. If the numerator and the denominator of the rational function have no common real zeros, if d of c equals 0 and x equals c is the vertical asymptote of the rational function, if the numerator and denominator of the rational function share common real zeros, they share linear factors for each shared real zero, and the rational function can be reduced by canceling these common factors, Bottom line is simplify first, factor the top, factor the bottom, then decide if there's any vertical asymptotes. Okay, horizontal. These are the ones I want you to write down. Okay? For horizontal asymptotes, a rational function with a numerator degree less than the degree of the denominator. So if the top degree is lower than the bottom degree, yes, you have a horizontal asymptote at y equals 0. Number 2, a rational function with numerator degree equal to the degree of the horizontal. So if the degree of the numerator and the degree of the denominator are the same, you look at the leading coefficient divided by the leading coefficient. And then the last one, if the rational function, the numerator degree is greater than the degree of the denominator, there is no horizontal asymptote. So bottom line, you need to look at the top, look at the bottom, and decide, is the top lower than the bottom degree? Are the degrees the same? Or is the degree greater than the degree of the denominator? Those are the 3 scenarios. And again, those are just a lot of words. Just write down the gist of it.
So there's going to be 2 horizontal asymptotes.
Okay. Okay, so let's look at this one. Find the vertical and horizontal asymptotes. I'm going to give you a few minutes to start first. Now that you know your vertical and horizontal rules, if you had f of x equals 3x squared plus 3x minus 6 over 2x squared minus 2, I'm going to ask you to remember factor first. Factor first. I'll give you a minute or two to get started. If you're still tough on factoring, there's a lot of resources in Appendix A that's going to help you with factoring. Okay, let's see if we got the first step. Factor the numerator and denominator. If you factor the numerator, 3x squared plus 3x minus 6 becomes 3 times x minus 1 times x plus 2. The denominator, 2x squared minus 2, factors to 2 times x minus 1 times x plus 1. Which means the x minus 1 and the x minus 1 cancel, simplify to 1. Now, what can the denominator not be? Negative 1. The denominator cannot be negative 1. Again, I can teach you vertical and horizontal asymptotes, but the factoring is going to be the tough part. It's an algebra where it always goes back to. Okay there? Yeah, I'll show you something. But the denominator cannot be negative 1. It's negative 1 plus 1 here. So, when it reduces to or simplifies to that, there's a vertical asymptote at x equals negative 1. Therefore, x equals negative 1 is the only vertical asymptote. So, before we do the horizontal asymptote, what is the degree of the numerator? 2. What's the degree of the denominator? 2. When they're equal, listen carefully, is there a horizontal asymptote? Yes. What is it? It's the leading coefficient divided by the leading coefficient. 3 over 2 would be the horizontal asymptote. So when they're the same, it's the leading coefficients, 3 over 2. So is there a horizontal asymptote? Yes. Where is it? 3 over 2. And the answer would be vertical asymptote at x equals negative 1. It's a vertical line. Horizontal asymptote at y equals 3 over 2. Okay? So if you remember those rules, you're able to find vertical and horizontal. And if you're ever stuck and not sure, what can you do? Just graph it. Let's see what it looks like. Okay? So let's go to our calculator. And let's see what this thing looks like. So I'm going to go to my calculator. I'm going to go to y equals. I'm going to get rid of that old equation. I'm going to turn off the plot by going up to it and hitting enter. Be careful when you graph rational, put them in parentheses. So parenthesis 3x squared plus 3x minus 6 in parentheses divided by parenthesis 2x squared minus 2 close parenthesis. Now, the good news is we can graph it to see what it looks like. The bad news is you got to figure out the window. Now, to figure out the window, we need to see x equals -1. So we got to go x beyond -1. And y, we have to see 3 over 2. So that's just 1.5. So a standard window of -10 to 10, -10 to 10, will that let me see everything? How do I do a standard window again? Zoom 6. So a standard window would let me see this pretty well. And let's look to see what we got. Where was the vertical asymptote? -1. Does it look like the graph comes really close but doesn't touch -1? Got it? What was the horizontal asymptote? What was it? 3 over 2, which is 1.5. 1.5 doesn't look like a horizontal asymptote of 1.5. So the good news is you can always check. You can always go to the calculator and check. Okay? We should be getting very comfortable with our best friend, the calculator. Okay? A function f is bounded if the entire graph of f lies between two horizontal lines. The only bounded polynomials are constant functions. Many rational functions are bounded. Okay? So if I had a company that manufactures computers or established that a new employee can assemble NFT components per days after T days of on-the-job training, where you have NFT equals 50T over T plus 4, but T has to be greater than or equal to 0. What I want you to do is that we're going to do the graph from 0 to 100, and I want you to tell me, are there any vertical or horizontal asymptotes? So here's our new problem. Are there any vertical or horizontal asymptotes? But remember, we're only looking at 0 to 100. We're only looking at 0 to 100. My question is, are there any vertical or horizontal asymptotes? And our domain is 0 to 100. So there's the function. We're going from 0 to 100. Our only thing we're looking at, are there any vertical or horizontal asymptotes? A minute or two. Are there any vertical or horizontal asymptotes in between 0 and 100? Okay, so let's talk about vertical asymptotes. Do we have any vertical asymptotes? Where? Where? What would it be? T equals -4. So are we agreed that there is a vertical asymptote at t equals -4? Are we agreed there? But does it fall between 0 and 100? So we're not worried about it. But there is one. But we're not worried about that. Okay? Let's talk about horizontal asymptotes. Now again, what's the degree of the numerator? What's the degree of the denominator? When they're the same, do we have a horizontal asymptote? Yes. What is it going to be? It's going to be n of t equals 50 over 1, or just 50. You can just call it y. And this problem is n of t. Okay? So again, just kind of know your rules. Now, if I wanted to graph this, let's practice graphing this. Let's go to y equals, and let's put 50x divided by, but remember that denominator needs to be in parentheses. So 50x divided by, parenthesis x plus 4. Now, I'm going to go ahead and give you the window. We already know x has to be between what? 0 and 100. So that tells us when I go to window, x is between 0 and 100, counting by tens. And I've already played around with it, so I'll help you out a little bit. Y is also going to be 0 to 100, counting by tens. Zero to 100, 10, 0 to 100, 10. Hit graph and verify that there is a vertical asymptote at 50. Horizontal. Horizontal asymptote at 50. When I hit graph, it looks like it's coming close but not approaching. 50 would be 10, 20, 30, 40, 50. Does it look like there's a horizontal asymptote at 50? Okay. So, I'm trying to do slides real quick. There's a horizontal asymptote at y equals 50. And if you graph it, we can see it. We okay? $1.4